Least squares minimizes the residual sum of squares, so adding another term can never raise the training mean squared error. A higher order polynomial will always fit the observations at least as well as a lower order one. That mathematical fact creates a statistical danger. The extra flexibility may follow accidental features of this sample rather than stable structure in the population. Overfitting means fitting the training data extremely well while predicting new observations poorly. The apartment example shows the trap. As the polynomial degree rises from a straight line to a very flexible curve, the training error falls monotonically. The most elaborate model therefore looks best if we judge it only on the observations used to estimate it. Yet the degree 15 curve produces implausible forecasts for large apartments. A smaller training error is guaranteed by added flexibility. Better out-of-sample prediction is not. The decomposition explains why prediction error does not fall forever. One part is squared bias, the gap between the true conditional mean and the average prediction made by the procedure. A second part is estimator variance, how much the fitted prediction changes across possible training samples. The third is genuine outcome uncertainty, which no model can remove. Model choice can trade bias against variance, but it cannot eliminate the irreducible noise in the outcome. A simple model may miss important curvature, creating bias, but it is relatively stable across samples. A complex model can reduce bias while becoming much more sensitive to which observations happen to be sampled. Genuine uncertainty stays fixed, so the model selection problem is to balance only the first two terms. This is why neither the most rigid model nor the most flexible model is automatically best. We want the point where their combined contribution to prediction error is smallest. The bias-variance trade-off changes with sample size. More complex models usually lower bias and raise variance. Simpler models do the reverse. With more observations, coefficient estimates become more stable, so we can afford greater flexibility. In the simulation described here, a linear model wins with the smallest sample, a quadratic wins with a larger sample, and a cubic wins with the largest. Complexity is therefore not an intrinsic virtue or flaw. It must be judged relative to the information available. The diagram gives the visual summary. Squared bias falls as complexity increases while variance rises. Their sum, the mean squared error apart from genuine uncertainty, forms a U-shaped curve. The best model sits near the bottom, not at either extreme. Notice that this optimum is about expected performance on new data. Training error alone would keep moving downward and would push us too far to the right into the high variance region.